In this presentation, we're going to go over thermal setting resins. We're going to talk about types of resins, base materials, manufacturers, byproducts, and uses. So what are resins? They're natural occurring resins, and there's also man-made resins. We use mostly man-made resins in our industry, but natural occurring resins, are things like tree sap. They've been used for years before synthetic resins were found, and they were used for things like sealing barriers, so they'd tar the insides of ships with pine pitch to make them watertight. They're also used as glues, so they were kind of the original glue. If you go out to a tree that has sap coming out of it, it's sticky. If you allow it to dry and harden, it gets hard, and it makes a pretty good glue. So that would be a natural resin. Man-made resins are better. They're stronger. They're more durable and more resistant. And there's kind of two types of resins. There's thermoplastic resins and thermal set resins. Thermoplastic resins, if you've taken orthotics, are used to make thermoplastic AFOs and all the sheet materials that you have. So thermoplastic resins are the type that melt when you heat them up, and then you can reform them and shape them. When they cool, they hold that shape. So that's a thermoplastic resin. Thermal set resins are resins that, when you mix two parts together, they combine together and a chemical reaction happens, and it creates a new material that's synthesized from the two different base components. So thermal setting resin produces heat when that chemical reaction happens, and that's why they call it thermal setting, is because it's producing heat as the resin sets. And that's typically what we use in prosthetics mostly. There's different types of thermal setting resins, and they all are used for different purposes, and they may look very similar. They're all liquids. They have 2 or 3 parts that you mix together. They set off and they make a hard plastic usually. But they all have different properties and different uses. And the basic ones we use are polyester resin, epoxy, vinyl ester, and acrylic resins. And these are all different, and they all have different characters, and they all have different working properties when you're using them. We're going to do a video, and I'm going to show you a basic video on casting some polyester resin. And it's just basically pouring a multi-layered block of polyester resin. And this is not something you're typically going to do in the prosthetic field, but it's a good tutorial video and gives you some idea of just basic working properties of the resins and how you mix them and how you set them off. So it's a nice video for that. It's going to take me a second here to get it converted over to the video mode. And this is produced by TAP Plastics. It takes about 7 minutes to go through.
This video segment will show you how to cast embedments in clear polyester resin. You can get further information and more ideas from the book, Cast and Craft Idea Book, available in our stores or from our website. Most of the steps shown here would also apply to easy cast, clear casting epoxy, with the exception of the mixing ratio. We will demonstrate using rigid molds such as this one here, since they are most commonly used for embedding. They can be purchased from our stores or from our website also. Polyester and epoxy can also be used in flexible molds as well. Even though casting resin is a do-it-yourself product, appropriate safety precautions should always be followed. The resin has a very distinctive odor, so should be used outside or with adequate ventilation. Never use near an open flame. Wear protective gloves and protect your work surface with a plastic trash bag or some other plastic film. Clearlight casting resin is a crystal clear polyester resin with low viscosity, as you can see here. Polyester resin hardens with the addition of MEKP catalyst. The amount of catalyst determines the speed of the cure. Too much catalyst and the resin will overheat and crack. Too little and the part will not cure properly and will remain sticky. For that reason, graduated measuring cups are important, as well as flat-sided stir sticks. The cups carried by tap are completely reusable. Do not use wax cups because flecks of wax will be visible in clear castings, as you can see in this piece. Let's begin. We will demonstrate with this mold. Many molds such as this show their total volume on the bottom of the mold. This helps you mix the proper quantities of resin. We will embed these coins and pour a colored background to create this part. This will require 3 pours. Since this is a 9-ounce mold, we will mix 3 ounces for our first layer. Keep in mind that the first layer in the bottom of the mold will be the top of the cast piece, so think upside down as you work. The amount of catalyst to use depends on the temperature and the volume of the resin and the room working temperature. More details are contained in the Cast and Craft Idea book. We will use 10 drops per ounce or 30 drops total. Thorough mixing is critical. Don't worry about introducing bubbles. They will release later. After adding catalyst, you will notice a color change. This tells you that the catalyst is working. The resin will return to a clear color as it cures. Now pour the resin into the mold. No mold release is required because these are polypropylene molds. If we added the coins now, they would sink to the bottom and detract from the final appearance. Remember, the bottom of the mold will become the top of the cast part. So we must wait for the resin to gel. This takes anywhere from 15 minutes to 1 hour depending on volume, catalyst ratio, and temperature. Before the resin fully hardens, it reaches a gel stage somewhat like the consistency of Jell-O. This is the time to pour the next layer. Frequently check for gel with a stir stick or by slightly tipping the mold. Polyester resin shrinks when it goes from gel stage to full cure. So if you wait too long, the resin will shrink away from the sides of the mold and your next layer will encapsulate the first layer, as you see here where we are pouring a layer of black onto the clear layer. Once this part hardens, it will need to be sanded to remove the black layer that has surrounded the surface. The resin has now gelled, as you can see, so we are ready to add our embedments. If we were to just lay the coins or other objects down on the gelled resin, we would trap air bubbles. This piece was done that way, and you can see the bubbles clearly. To prevent air bubbles, we will mix another 3 ounces for the next layer. Pour half of the mix into the mold. Use the other half to coat each coin, then lay the coin down in the mold in such a way as to force the air out from under the coin as it is lowered. This will squeegee the air out from under the coin or whatever object you are embedding. We now wait for this layer to gel so that we can add our colored background. The second layer has gelled, so we are ready to add the colored background. We will mix 2 ounces of resin and add 4 drops per ounce, since the heat from the first 2 layers will help cure this final layer. We will use black super pigment, and we will use as little as possible because too much pigment can inhibit the cure. Once mixed, pour it into the mold. For transparent colors, use one of the dye colors available at tap. Polyester resin stays tacky in the presence of air for a long time. There are a couple of solutions to this. One is the use of Cast and Craft resin spray. This coats the tacky resin and seals it off so that it cures completely. The other solution is to place the part in a warm area such as a sunny window and give it more time to cure. This can take as long as several days. Finally, surface curing agent can be added to the last layer to get a complete cure. However, this only works if the layer is dyed or pigmented, since it will create a hazy appearance in the clear resin. Well, our part has cured, and it is ready to remove from the mold. You can tell the resin has pulled away from the mold by the light color of the mold compared to when it was first poured. This indicates a complete cure. Pulling the part out of the mold prematurely would harm the finish. With these basics, you are now ready to experiment and develop your own techniques and methods using Clearlight casting resin or Easy Cast epoxy casting resin.
Tough, tough plastics, the fantastic plastic waste.
That short video had a lot of good information, and you may want to, after you've worked with resin for a while, go back and watch that video again, because some of the tips they had in there for curing resin when it's not covered by plastic or a PVA bag can be helpful. And after you've worked with it for a while, it'll probably sink in a little bit better some of the importance of some of the smaller facts that were in that video. So I encourage you later on, after you've worked with resin for a while, to go back and watch that video again. Now we're going to go over the different types of resins that we use one by one. And the first one is polyester. This resin has been around for a very long time, and it was used in prosthetics extensively for quite a long time. And it's still used today, but just not in as much volume as it used to be. There's better resins out there now than this resin is, but it's still used somewhat. It's very cheap, it's very economical. This is kind of a chemical makeup of it, and you can see that there's S's and B's and A's, and the S's are the styrene molecules, and they bond together with the different molecules and make sort of this very crystalline square type of structure. It's a very rigid resin. And it doesn't have a lot of flexibility, so it'll flex so far and then it'll crack. So when you're working with polyester resins, they're peroxide-based catalysts. So when you read the catalyst tubes or the little jug of catalyst that you get along with the resin, it's going to say peroxide on the side of it, and that's what causes or catalyzes the resin and makes it start to turn into a hard plastic. It tends to be easily saturating when new, so when you go to wet out your lamination and the fibers and the fabric that you're trying to impregnate with resin, it goes into those fabrics pretty easily when it's new. When it sits in the shelf for over 6 months, it starts to get thick and kind of gummy. When that happens, it's hard to laminate with it. So you always want to keep fresh resins. All your thermal setting resins have a shelf life, and so you don't want them sitting on your shelf for 6 months or a year before you use them. You want to use them while they're fresh, and you'll have the best results with that. It has adjustable flexibility, so you can change the amount of flexible resin and rigid resin and get different flexibilities out of it. It bonds very well to fiberglass, so if you're just doing a fiberglass socket, you're not going to have carbon fiber in it. You'll probably get a stronger socket using the polyester than some of the other resins. It has good adhesion, so you can use it as a glue. If you need to bond something together, you can mix some of it up, use it as a glue. It has good cold joint strength, so what that means, a cold joint would be a joint that when you try to bond something and the one piece has already been bonded, has already set off and is hardened, and you come back the next day and you want to bond another piece to it, that's a cold joint because there's no chemical bond between the two pieces of resin. A hot joint would be a joint that there's both the pieces are still setting off and they're bonding together chemically. So this has good cold joint strength as long as you rough up the surface and abrade it so you have a mechanical bond between the two pieces. It's water resistant after it cures. It's also somewhat moisture tolerant as it cures, so if a little moisture gets into it, it won't hurt a whole bunch. But if you do have moisture in your lamination, you can get some defects and have some problems with it. So moisture, when you're dealing with resins, is pretty much always a bad thing, but this type of resin is slightly tolerant of it. But it's best to not have any moisture in your resins when you're laminating. It yellows in UV light, so if you take a piece of polyester resin, you put it outside, and it's clear, after it sits in the sun for a while, it's going to turn yellow and change colors. And that's important to know because when you're making a prosthesis and you're color matching, it may match perfect today, and then your patient goes out to the beach in the sun and it comes back and it's yellowed and it's changed colors. So that might not be a real good quality for a resin. It's very economical, though. It's cheap. It's one of the cheapest resins out there. It's used in all kinds of industries. And then it does have a shelf life on it, so it will gel out without the use of catalyst. So if this sits on your shelf, it's going to start to set off without the catalyst because it's already been pre-promoted and it just needs the catalyst to finish off the chemical reaction. So it will slowly set in the jar while it sits on your shelf. So you have to be careful of that. The mixing ratios, there's a rigid polyester and a flexible resin. Typically, the lower extremity prosthetics are made out of what's called an 80-20 mix. You used to have to mix this in the correct ratios. Now you can purchase it pre-mixed, and most is sold in an 80-20 mix, pre-mixed for you. If you do upper extremities, you want them a little bit more flexible, so they'll do a 70-30 mixed. If you do the 70-30 mix, you have to oven cure the polyester resin. So after you laminate it, it will set, but it'll still kind of gas off and have chemicals in it that haven't completely set yet, and those will wick away and get into the patient's skin. So what you have to do is you have to cure it in the oven to force it to complete its cure time. And when you do that, then it hardens up and it's safe for the patient to use, but you must cure anything over a 70-30 mix. The catalyst is usually 3%, so 3% is your standard mix. So if you have 100 grams of resin, you're going to put in 3 grams of catalyst. And then you'll have a promoter, and the promoter is a brownish liquid that's very dangerous, and it's not good at all to have in your system. It's quite poisonous, but usually do 5 drops per 100 grams of resin with the promoter. So that's kind of when you mix up polyester resin, you first have the resin, then you have the catalyst, and then you have the promoter that you have to put in that certain ratio. You want to, of course, mix it well, and then the set time is about 7 to 10 minutes. So it sets off pretty fast, and you have to work it pretty quickly. You don't have a lot of time to spare when you're working with polyester resins. Some of the applications, industries use it for glue, for fiberglass boats, for fiberglass cars, furniture. It's used in Bondo. It's the main ingredient in body fillers and things like that usually. It's used all over the place, and that's why it's so affordable and so cheap. Now, the next one we're going to talk about is epoxy. And epoxy is a thermosetting resin, and it's mostly used for a really strong adhesive. It has great adhesive qualities. It sticks. Once it sticks to something, it stays there. It can bond to metal. It can bond to porous things like brick or wood, laminate, anything. It just really bonds really well, and it's very strong. It's also very difficult to work with. They have certain characteristics that you have to, when you're working with them, they can take a long time to set, or they can set very quickly. There's hundreds of different types of epoxies, and you have to make sure you're working with the right type and understand how it works and all its properties and working properties when you're working with it. It has sort of a strange network type of molecular structure, and it's not real structured like the polyester resin is. So all these little molecules can get in all the little nooks and crannies of the surface and really bond well to them. So it has a really good, strong bonding characteristic to it. It makes a really strong carbon fiber type of a resin. It's not hardened by the peroxide like polyester is, but it's hardened by the amine hardener. And you have to be very precise. Usually the mixing ratios on epoxies are like 1:1 or 1:2 or 1:3. So and they have to be very precisely done. If they're not, then the epoxy won't set correctly. So you have to be very, very careful when you're measuring out epoxies. They tend to be difficult to saturate because they're a thicker, more viscous fluid, and they're a little bit harder to laminate with. You can heat them up and warm them before you laminate to try to get the viscosity down, but they're still difficult, and when you heat them up, they're going to increase the set time also, so you're going to have to work faster. Tend to be extremely strong. They bond to all kinds of materials. They have very, very good cold joint strength, so they're very strong if you want to do a cold joint. They tend to be very expensive, and they're definitely challenging to work with. When you mix them, it's usually a 50-50 mix. It may be a 2-to-1 mix. You got to be accurate in your measurements. Very sensitive to temperatures, and very, very viscous. And they also have long cure times, sometimes like 24 to 48 hours sometimes. So we don't use them extensively, but there are some companies that do use them. You can make extremely lightweight, strong devices with them. Just very difficult to work with. Some of the applications are glues, resin, paints, computer insulators. One of the interesting things, we do use epoxies for just bonding things a lot in our industry, not so much for laminations. And if you get some epoxy on your hands or on the table, somewhere where you don't want it to be, before it hardens, you can clean it up with vinegar. And that's an important thing to remember. Just have a little bottle of vinegar around, and it'll clean the epoxy right up and kind of dissolve it. So that's a nice cleanup tip. The next one we're going to talk about is vinyl ester, and this is a combination of a polyester base resin and then some components of epoxy resin to create it. It's basically a more economical, easier to work with type of epoxy resin that's a little bit stronger. And this resin has taken over the O&P industry in the past few years. It's economical, it's strong, and it also has a bit of flexibility to it. So where a polyester resin, you might hit it with a hammer and it might crack. A vinyl ester resin, you'll hit it with a hammer and it'll just kind of bend and bounce back and not crack. So it's a little more durable. And if you remember back to the other picture, the vinyl ester resin had a bunch of, pretty much every molecule was connected to another one. This one has some spaces between it, and the styrenes are few and far between. So that gives it its flexibility and its toughness, and just makes it more resilient than other resins. Some of the working qualities, it uses a peroxide-based catalyst just like the polyester resin did. It has very good saturation, so it has low viscosity, so it works very easily. It's strong, it's durable, and it bonds well to carbon. So if you're going to do a carbon socket, this is a good one to use. It has marginal bonding ability to fiberglass and Kevlar. So if you're going to use this to bond, make a fiberglass socket, it's probably not the wisest idea. We have a sample in the O&P lab of some different layups, and you'll see that the ones that were bonded with fiberglass and the vinyl ester are not very strong at all. So you may not want to use this for fiberglass. It has poor cold joint strength, so if you're doing a cold joint and you want to bond the resins together, it's probably not the best one to use for that either. It's very inexpensive. It's extremely UV sensitive. This resin will turn brown if you take it out into the light very much. So you would not want to use this in any type of clear laminations that are going to go outside. They're very water resistant after curing, and it's heat moldable after curing. So you can actually heat this resin up and mold it a little bit after it's cured without hurting it too much. So that's something kind of interesting. Most of the other thermal setting resins don't have that property. Vinyl ester mixing, it's 3% hardener, 3 grams per 100. Mix until the hardener has dissolved, and then 5 to 10 minute set times. Sticks well to many surfaces, low viscosity. Some of the applications, speedboats, and they use it for water pipeliners since it's very water resistant. And the speedboats, they just get pounded all the time, so that flexibility is a good thing for them, so they use that resin in those. Some of the advantages and disadvantages of different resins, the top is polyester. So the advantage of polyester is that it's easy to use and it's very cheap, so it's a low-cost resin. Some of the disadvantages, only only moderate mechanical properties, so it's not extremely strong, may crack. High styrene emissions, so what that means is it's going to put a lot of styrene out into the air, which isn't really good to breathe. High cure shrinkage, so it's going to shrink as it cures. Like that video said, they showed that the clear resin, after it cured, shrank away from the mold. So it does shrink some. And then it has a limited range of working time. So you're really stuck with that 7 to 10, 15-minute range. You don't have much more working time than that to work with it. The next one down is vinyl ester. It has a very high chemical environmental resistance, so it's not going to be affected by chemicals. Higher mechanical properties than polyesters, so it's stronger, it's more flexible, more durable than the polyester. Some of the disadvantages is it may require, it again has the high styrene count to it, or content, so it's going to let out the styrene molecules. And then it's a little bit higher cost than polyester, but not extremely high, so it's still very economical to use that. And then it also shrinks quite a bit for while it cures. Then epoxies, some of the advantages of epoxies is it has a high mechanical and thermal properties, so it's very strong. It's really resistant to water. You have long work times, but that can also be a disadvantage if you're in a hurry to get something done. You really don't want to wait till tomorrow for something to set off. And then it has low cure shrinkage, so it doesn't shrink like the other ones do. So that can be a good thing. The disadvantage of the epoxies is very expensive. It's very critical your mixing is right, and then it also has corrosive handling. So if you want to ship epoxies in the mail, you may have to have special packaging or special handling to ship certain epoxies in the mail. And that again is going to make it more expensive. And the last type of resin we're going to talk about is acrylic. And acrylic's a little bit different. It's a clear resin that's not affected by UV light. So they use it for all kinds of stuff. Like some of the nails, like when ladies get their artificial nails put on, the smell that you smell coming out of those shops is actually the acrylic resin curing. So you'll have a lot of that odor when you're using acrylic resins. So some of the working properties is they're also a peroxide-based catalyst. They saturate very well, so they're low viscosity resins. They're strong, they're durable. They bond really well to carbon, so that's good for a lot of the prosthetics things that we do. They have marginal bonding to fiberglass. They don't bond very well to fiberglass. They have really good cold joint strength, and this is how they're somewhat different than all the rest of the resins. These resins actually have a chemical bond that happens, so when the new resin is placed over the top of the old resin, it actually melts into the old resin and makes a chemical bond that's very strong. So that's a good thing. They tend to be very expensive, and they are very UV resistant, so they're not going to yellow. You could put these outside and they're going to stay clear and not yellow. So if you're doing a cosmetic lamination, you're going to use clear resin over the top of a very light color like light blue or something. These won't turn yellow and ruin the whole prosthesis in the sunlight. So that's a really good attribute of acrylic resins. They are very sensitive to moisture during curing. So if you have any moisture in your cast, in your PVA bags, in your positive model, it's going to destroy the whole lamination. So you have to be very cautious about keeping moisture out of your lamination while you're working with acrylic resins. And they're slightly water sensitive after curing. If you take acrylic and you place it in water for a long time, it'll kind of get cloudy looking and swell some. So you don't really want to have them in water all the time. When you mix acrylic, it's 2 to 3% hardening powder. Mix until the powder is dissolved. It has to be degassed, and this is something different also when you work with acrylic resins. The acrylic lets off a gas, and if it does that while you're laminating, you're going to have air bubbles throughout your whole lamination. So to get rid of that, you're going to put it in a vacuum chamber, and the vacuum chamber is going to pull the gas out of the resin before you laminate with it. And the reason you can do this is because the acrylics have a longer set time. So it takes about 30 to 45 minutes as compared to 7 to 10 minutes with the other resins. And that gives you time that you can place your resin into a vacuum chamber for 4 to 7 minutes to get that air out of the resin before it gets into your lamination. And that's an important step when working with acrylics. They also tend to be very sensitive to heat buildup in thick areas. So if I have a model that I'm making and I'm pulling or laminating a socket over it, and I leave a lot of resin in one spot and it pools up and it becomes thick in that area, the heat is going to make the resin set off too quickly and it's going to bubble and crack in that area. So you have to make sure that you don't have too thick of a lamination anywhere. If you do, you could have some cracking and bubbling problems when it starts to cure. You can control the heat while you're laminating by bathing the PVA bag in some acetone, and as it evaporates, it'll cool down the lamination. But if you correctly build it up and just get rid of all the thick areas, you shouldn't have to worry about that. Applications, they make jewelry out of them, windows, paint, dentures, bone cement for doing hip replacements and things like that are made out of acrylic resins. That's all I have for the resins. If you have any questions, feel free to contact your instructor.